Welcome to Lasea class. I am your teacher, Jan Lasea. Today, we study the KNearest Neighbor classification in machine learning. Classification is a task that involves arranging objects systematically into appropriate groups or categories, depending on the characteristics that define such groupings. The use of classification is to determine the category to which an unseen observation belongs, depending on the information of a training dataset with appropriate labels. The classification has a predetermined name or label. The classification is a supervised machine learning task. There are plenty of algorithms to learn in machine learning. Under the classification, let us understand the KNearest Neighbor classification. Types of systems of machine learning. The supervised learning learns from previous examples. For example, a car has 4 wheels, therefore, if a new object has 4 wheels, it could be a car. The data that you fed into the algorithm with the desired solution are referred to as labels. Some examples of supervised learning, such as the KNearest Neighbor, linear regression, logistic regression, neural networks, support vector machines or SVM, decision trees, and random forest, to name but a few. On the other hand, the unsupervised learning, it infers a grouping without any label to learn from. For example, a list of items all have roots and are made of wood, so they should go into the same group even though they lack a name. The data is unlabeled. It means it finds patterns, solutions, and clustering. Some examples of unsupervised learning under the clustering, such as k-means, hierarchical cluster analysis. Under the association rule learning, such as ECLAT, a priori. Under the visualization and dimensionality reduction, kernel PCA, T-distributed, principal component analysis, to name but a few. The KNearest Neighbor algorithm is a non-parametric supervised learning method used for classification and regression. Non-parametric means it is not based on either the mean and variance. The KNearest Neighbor algorithm is a lazy algorithm because no real learning is done at the training time, just data recording. The variable k is a hyperparameter that specifies the number of nearest neighbors that the algorithm has to consider in order to figure out an answer or prediction. Choosing the value of k. The smaller the k parameter, the more the algorithm will adapt to the data you are presenting, risking overfitting but nicely fitting complex separating boundaries between classes. The larger the k parameter, the more it abstracts from the ups and downs of real data, which derives nicely smooth curves between classes in data, but does so at the expense of accounting for irrelevant examples. As a rule of thumb, first try the nearest integer of the square root of the number of examples available as a k parameter in the KNearest Neighbor algorithm. For instance, if you have 1000 examples or 1000 records, start with the square root of 1000, which is 31. So k is equal to 31. And then decrease the value in a grid search backup by a cross validation. some issues in cases where we choose uneven k. For example, if k is equal to 4, we may encounter a situation where 2 points belong to a class A and the other two to a class B. And then therefore, there is a possible a tie. In this case, it is not possible for us to decide whether to assign our new sample to either class A or class B. So therefore, we need to choose a add value for the value of the hyperparameter k, not even. Let us understand the algorithm behind the k-nearest neighbor just by looking at this figure. There are two groups, namely the red triangles and the blue squares. What will be the classification of this green dot as a test example? Does this green dot belongs to a red triangle or a blue square? The KNearest Neighbor algorithm will compute the nearest distances either using metrics such as the Euclidean distance, the Manhattan distance, or the Chebyshev distance. For example, if we choose a value for k which is 3, then the algorithm will select the 3 nearest neighbors to the green dot. And we can look at the figure that the 3 nearest neighbors to the green dot are 1 blue square and 2 red triangles. And then we apply majority of votes by counting the highest number of groups that this green dot might belong to. Therefore, the class or category of the green dot is a red triangle, because if we count the number of red triangles, we have 2 red triangles versus 1 blue square. Another example, if we choose the value of k equals to 5, then the algorithm would select 5 nearest neighbors to the green dot. And we can identify them as 1, 2, 3, 4, and 5. And we have 3 blue squares plus 2 red triangles. If we apply the majority of votes, therefore, the class or category of the green dot is a blue square, because there are 3 blue squares versus 2 red triangles. And that is how simple the steps, how the k-nearest neighbor will classify an instance whether it is a red triangle or a blue square. Overfitting the training data. Overfitting happens when the model is too complex relative to the amount and noisiness of the training data. The model has a high variance. For high variance models, the performance of the model on the validation set is far worse or very low than the performance on the training set. If we look at this graph, the coefficient of determination, or R square, of the training is very high. But the coefficient of the determination, or R square, of the cross-validation is very low. Therefore, the model has a high variance and overfits the data. The possible solutions for overfitting are: number 1, to simplify the model by selecting one with fewer parameters. For example, a linear model rather than a high-degree polynomial model, or by reducing the number of attributes in the training data, or by constraining the model. Number 2, gather more training data. And then finally, reduce the noise in the training data. Either you fix the data errors or remove outliers. Underfitting the data. Underfitting occurs when your model is too simple to learn the underlying structure of the data. The model has a high bias. For high bias models, the performance of the model on the validation set is similar to the performance on the training set, which are both low. If we look at this graph or figure, the coefficient of determination or R square of the training is similar to the cross-validation, which are both low. Therefore, the model has high bias and underfits the data. The main options to fix this problem are: number one, selecting a more powerful model with more parameters. Number two, feeding better features to the learning algorithm, or we call this the feature engineering. And then finally, reducing the constraints on the model, for example, reducing the regularization hyperparameter. So what is then the best model? The best model is a trade-off between the bias and the variance. Let us look at this diagram or the figure or the picture. The best model is around the top or the maximum of the cross-validation curve, which is around here. This is the top of the validation curve, or we call this as the maximum. And this is the best model. It is a trade-off between the bias and then the variance. We call this the validation curve. The following are the essential features of the validation curve. Number one, for very low model complexity or a high bias model, the training data is underfit, which means that the model is a poor predictor both for the training data and for any previously unseen data or validation data. Number two, for very high model complexity or a high variance model, the training data is overfit, which means that the model predicts the training data very well but fails for any previous unseen data or the validation data. Number three, for some intermediate value, the validation curve has a maximum or top of the curve. This level of complexity indicates a suitable trade-off between the bias and variance. Ideally, both the validation curve and the training curve must look similar as possible. And then we look at the validation curve, the, the top of the validation curve or the maximum as the place that we can find the best model, which is a trade-off between the bias and the variance. The example dataset to classify using the KNearest Neighbor algorithm is the diabetes dataset. The diabetes dataset consists of fields, namely the number of pregnancies, glucose, blood pressure, skin thickness, insulin, body mass index or BMI, diabetes pedigree function, age, and outcome. There are 768 records. The dependent variable y or target is the outcome. Under this outcome, it has two possible values. A1 indicates positive for diabetes. A0 indicates negative for diabetes. The independent variables x or predictors are the number of pregnancies, glucose, blood pressure, skin thickness, insulin, body mass index, BMI, diabetes pedigree function, and age. Choosing the value of k by fine-tuning. The following Python codes will determine the highest validation accuracy for odd numbers of k from 1 to 100. The for loop will repeat instantiating the KNearest Neighbor classifier with k neighbors and gathers the validation accuracy, and in the end, it determines the highest validation accuracy with k value. The results are shown on this graph. The best k value is around 11 with validation accuracy of 81.82%. Another way to choose the value of k is by using the sklearn grid search CB. The following Python codes will determine the highest best score for odd numbers of k from 1 to 100 using the sklearn library grid search CB class. The results are highest best score of 78.18% with k equals 13. Using the scikit-learn or sklearn validation curve. A validation curve is an important diagnostic tool that shows the sensitivity between the changes in a machine learning model's accuracy with change in some parameter of the model. A validation curve is used to evaluate an existing model based on hyperparameters, and it is not used to tune a model. This is because if we tune the model according to the validation score, the model may be biased towards the specific data against which the model is tuned, therefore not being a good estimate of the generalization of the model. We look at the graph of the validation curve under the cross-validation score, which is represented by this green curve. We can say that the best model is around the maximum or top of the green curve, which is around here with the number of neighbors at 11. Here we can estimate that if k is equal to 11 around here, this is the best model for the KNearest Neighbor classifier for the diabetes database. It is a trade-off between the bias and variance. This is the summary finding the best key value of KNearest Neighbor classification for the diabetes dataset. The best value for k is 11, but the validation and training scores are low, nearly similar, which is underfitting. Probably, KNearest Neighbor is not the best method for classifying the diabetes dataset. We can experiment other classifying algorithms such as logistic regression for classification, decision tree, random forest, extra trees, neural network, to name but a few. These are the codes for the KNearest Neighbor classification written in the Python programming language. At line number 32, it will load the diabetes dataset. At line number 35, it displays the total records. At line number 38 to 43, the fields glucose, blood pressure, skin thickness, BMI, and insulin data will replace if there are zeros, will be replaced by the mean value of the counted zeros or the none or not a number. At line number 47, it selects the following features for independent variable x, namely the number of pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and age. At line number 49, it selects the outcome as the y-dependent variable or the target variable. At line number 52 to 53, it splits the data into separate training and test data set. 20% will be allotted for the test data set and 80% will be allotted to the training data set. At lines number 59 to 63, it applies feature scaling. Standardization is a useful technique to transform attributes with a Gaussian distribution and differing means and standard deviations to a standard Gaussian distribution with a mean of 0 and a standard deviation of 1. At lines number 66 to 98, it performs fine-tuning the value of k from 1 to 100 and add numbers only. At lines number 101 to 111, it performs fine-tuning the value of k using the sklearn grid search CV from 1 to 100 and add numbers only. At lines 114 to 120, it chooses the best k value between the fine-tuning and the grid search CV. At line number 123, it fits the KNearest classifier to the training data set. At lines 126 to 133, it trains the KNearest Neighbor model. At line 136, it predicts the test set results. At lines 139 to 147, it evaluates the model. At lines 150 to 173, it plots the validation curve. At lines 176 to 197, it computes the confusion matrix. At lines 201 to 214, it plots the graph of the confusion matrix. Finally, at lines 217 to 249, the user inputs test data for prediction. Ladies and gentlemen, let us run and test. The total records is 768. It displays the graph of the fine-tuning from 1 to 100 with add numbers, and it chooses the value of k, which is 11, having a validation accuracy of 81.82%. The K value of 11 is around here with a validation accuracy of 81.82%. Next, it will fine-tune the value of K using the grid search CB, and it displays the best score of grid search CB, which is 78.18% with a K value of 13. The chosen best K value is 11. This graph shows the validation curve applying the KNearest Neighbor to the diabetes dataset. And then the validation curve, we look at the trade-off between bias and variance, and estimate the best model around the cross-validation score, which is the top or the maximum of the cross-validation score represented by the green dot, which is around K is equal to 11, which is around here. The best model, the trade-off between the bias and the variance. Next, it shows the graph of the confusion matrix. The total correct is 94 plus 32, which is 126. The total wrong, which is 13 plus 15, equals 28. Let us input some test data to predict. Please enter the number of pregnancies, 6. Enter the amount of glucose, 148. Blood pressure, 72. Skin thickness, 35. Insulin, 0. BMI, 33.6. Diabetes pedigree function, 0.627. Age of the person, 50. And predicted or prediction that the person has a diabetes. That ends our topic for today. I hope you are inspired in my class. Thank you for watching. God bless us.